On the 20th of October 2020, a NASA spacecraft reached out and touched an asteroid 200 million miles from Earth. Contact lasted 6 seconds. In those 6 seconds, the sampling arm did not bounce off the surface the way the models had predicted. It sank. It went in about 1.5 feet, and it kept going, until the thrusters fired and hauled the spacecraft back out into open space. The signal confirming any of this took more than 18 minutes to make the round trip. By the time the team at Lockheed Martin in Colorado knew the arm had touched down, the event had been over for a quarter of an hour. Nobody could have intervened. The spacecraft was on its own. What it grabbed in those 6 seconds weighed 121.6 grams, roughly the mass of a bar of soap. That material came home 3 years later. It went into a sealed laboratory at NASA's Johnson Space Center, and then into instruments at Goddard, at the Smithsonian, at the Natural History Museum in London. And what those instruments found in 121 grams of asteroid dust reshaped how we talk about where the ingredients of life came from. This is the story of that sample. How we chose the rock. Why the surface behaved like nothing we expected. And what was waiting inside. There are more than 1 million known asteroids in the solar system. The mission had to pick one. The selection came down to 3 requirements, and they fight each other. First, the asteroid had to be reachable. That means a near-Earth orbit, one that comes close enough that a spacecraft can get there and get back without an impossible fuel budget. Second, it had to be big enough to be stable. Small asteroids spin fast. Anything under about 650 feet across tends to rotate so quickly that loose material is thrown off the surface, leaving bare rock with nothing to sample. Third, and most importantly, it had to be dark, carbon-rich, the kind of primitive body that has not been cooked or crushed since the solar system formed, and might still hold the chemistry it started with. Asteroid Bennu satisfied all 3. It measures about 1,600 feet across. It circles the Sun every 14 months on a path that crosses our own, and it is one of the darkest objects we have ever visited. It reflects less than 5% of the light that falls on it. There was also a 4th reason, and it had nothing to do with chemistry. Because Bennu's orbit crosses ours, it is tracked as a potentially hazardous object. A 2021 analysis led by Davide Farnochia at NASA's Jet Propulsion Laboratory used the spacecraft's own navigation data to refine that orbit with far greater precision than telescopes alone could manage. The result put the cumulative probability of an impact through the year 2300 at roughly 1 in 1,750. The single most significant date is the 24th of September 2182, and even that carries odds of about 1 in 2,700. That date is worth holding on to. The sample capsule came down in the Utah desert on the 24th of September 2023, the same calendar day 159 years earlier. Dante Loretta, the mission's principal investigator at the University of Arizona, spent years building the case for this specific rock. The mission was named OSIRIS-REx. It launched on the 8th of September 2016. The name of the asteroid itself came from a 9-year-old boy in North Carolina, Michael Puzio, who won a public naming contest in 2013. He proposed Bennu, an ancient Egyptian bird associated with creation and rebirth. The spacecraft took 2 years to arrive. It reached the asteroid on the 3rd of December 2018, and almost immediately, the plan started falling apart. Every model built before arrival predicted the same thing: a surface covered in fine grains, something like a beach. Ground-based observations of the asteroid's thermal properties supported it. The rock appeared to be shedding heat in a way consistent with a coating of loose sand. The first close images showed boulders. Not a scattering of them, the entire surface. Rocks the size of cars, rocks the size of houses, and one slab more than 170 feet long, sitting near the southern hemisphere. The spacecraft carried a sampling head designed to work in fine material. It had been built and tested against a surface that did not exist. Then, on the 6th of January, 2019, the cameras caught something else. Bennu was throwing rocks into space. Small particles, a few inches across, launching off the surface. Some fell back into orbit around the asteroid, some escaped entirely. The asteroid was actively ejecting material, and no one had predicted that either. The most likely explanations are unglamorous and both probably contribute. Bennu's surface swings through a temperature range of more than 300 degrees Fahrenheit every 4 hours as it rotates, and rock that is heated and cooled that violently eventually cracks apart. On top of that, the asteroid has no atmosphere, so every micrometeorite that arrives hits the surface directly. A body this small has so little gravity that either process is enough to throw debris off it. The picture that emerged over the following months was of a body with almost no internal strength. Bennu is not a solid rock. It is a rubble pile, a loose aggregate of fragments held together by gravity so weak that a person standing on the surface could jump clean off it and never come back down. It spins once every 4.3 hours, and that spin has pushed material toward the equator, giving the asteroid the profile of a spinning top. All of this material is old. The fragments came from a much larger parent body, one that was shattered somewhere between 1 and 2 billion years ago. The rock inside those fragments dates to the formation of the solar system itself, which meant the sample was still worth collecting. The team simply had to find somewhere to land that would not destroy the spacecraft. The sampling system was designed for a target zone 160 feet wide. On Bennu, no such zone existed. The team spent nearly 2 years mapping every boulder larger than 3 feet across the entire surface. They narrowed the candidates to 4 sites and gave them bird names: Nightingale, Kingfisher, Osprey, Sandpiper. Nightingale 1. It sits inside a crater about 65 feet across in the northern hemisphere, and the material there appeared unusually fresh, shielded from the worst of the solar heating. The usable landing area inside it was about 26 feet in radius. The spacecraft, with its solar arrays extended, is about 20 feet wide. There was a building-sized boulder on the crater rim. The team named it Mount Doom. To reach the target, the spacecraft had to descend for 4.5 hours, navigate by matching live camera images against a stored map of the surface, and abort automatically if it drifted outside the safe zone. It executed all of it without a human in the loop. At the moment of contact, a bottle of nitrogen fired into the surface to blow material up into the collection head. And the arm kept descending. Kevin Walsh, a researcher at the Southwest Research Institute in Boulder, later led the analysis of what happened in those 6 seconds. The conclusion was that Bennu's surface has almost no cohesion at all. The particles are barely holding on to each other. His description of it was a pit of plastic balls. Step onto it, and you sink. The measurements backed him up. The spacecraft's thrusters, firing to push it away, excavated a crater 26 feet wide. A gentle contact and a short thruster burn moved more material than a substantial impact would move on Earth. If the retreat burn had come a few seconds later, the spacecraft would have kept going into the asteroid. 2 days after the touchdown, the cameras were turned on the collection head to photograph the sample. The images showed particles drifting away from it. The head had taken in so much material that a fabric flap, designed to seal it shut, was wedged open by larger fragments. Every small maneuver was shaking more of the sample loose into space. The plan had called for a careful measurement of the collected mass before stowage. That plan was abandoned. The team skipped the measurement entirely and moved directly to sealing the head inside the return capsule, 8 days after collection. They did not know how much they had. They only knew they were losing it. OSIRIS-REx departed the asteroid on the 10th of May 2021 and spent 2.5 years crossing back. On the 24th of September 2023, the return capsule separated and entered the atmosphere at nearly 27,000 miles per hour. It came down under parachute onto the Utah Test and Training Range in the desert west of Salt Lake City. A recovery team was waiting. They reached the capsule by helicopter, and before anyone touched it, they took samples of the desert soil and the surrounding air. A record of exactly what terrestrial contamination looked like at that spot on that morning, so that anything found later in the sample could be checked against it. The capsule was carried out, slung beneath a helicopter, and flown to a clean room assembled on the range. It was on a plane to Houston the following day. It was the first asteroid sample return in American history, and the largest sample of its kind ever brought to Earth. The spacecraft itself did not stop. It was renamed OSIRIS-APEX and redirected toward the asteroid Apophis, which will pass closer to Earth than our geostationary satellites in April of 2029. At Johnson Space Center, the collection head went into a sealed glove box flooded with dry nitrogen, so that no terrestrial air, moisture, or organic material could ever reach the sample. 35 fasteners held the head closed. 33 came out. The last 2 would not move, and the curation team could not simply reach for a tool from a hardware store. Anything entering that glove box had to be certified not to shed contamination into the material. They designed and built new instruments from surgical-grade stainless steel, tested them on a duplicate head outside the box, and only then went in. That process took nearly 3 months. The head opened on the 10th of January 2024. The total mass was 121.6 grams. The mission requirement had been 60. The analysis was distributed to laboratories on several continents. 2 sets of results were published together on the 29th of January, 2025. The first came from a team led by Daniel Glavin and Jason Dworkin at NASA's Goddard Space Flight Center, published in Nature Astronomy. They found amino acids. 14 of the 20 that terrestrial life uses to build proteins were present in the sample. They found all 5 nucleobases: adenine, guanine, cytosine, thymine, and uracil. Those 5 are the letters of DNA and RNA. Every one of them was sitting in asteroid material that has never been part of a living system. And they found ammonia at concentrations far above anything measured in terrestrial rock. Ammonia is a nitrogen source, and nitrogen chemistry is one of the harder steps in assembling biological molecules. The second result came from a team including Tim McCoy at the Smithsonian's National Museum of Natural History and Sarah Russell at the Natural History Museum in London, published in Nature. They were looking at minerals rather than organics, and they found salts. Specifically, they found an evaporite sequence, the pattern of minerals that forms when salty water evaporates and leaves its dissolved contents behind. Halite, sylvite, sodium carbonates, including a mineral called trona, which had never been identified in an extraterrestrial sample before. Those minerals only form one way. There was liquid water on Bennu's parent body. It was briny, and it evaporated. Put the 2 results side by side, and the sequence becomes clear. A large body in the early solar system held pockets of salty water. Organic molecules formed and concentrated in that water. The body was destroyed. Fragments reassembled into the rubble pile we visited, carrying that chemistry with them, sealed and unchanged for more than 1 billion years. There is one more measurement, and it is the one that matters most. Amino acids come in 2 mirror forms, left-handed and right-handed. The same atoms, connected the same way, arranged as reflections of each other. Chemistry that has no biological involvement produces both in roughly equal amounts. Life on Earth does not. Every organism on this planet, every bacterium, every tree, every person, builds its proteins almost exclusively from left-handed amino acids. The right-handed versions are excluded, and we do not fully know why. The amino acids in the sample were an even mixture, left and right, in equal measure. That single result separates two questions that had been tangled together for decades. The ingredients did not require life to form. They assemble on their own, in cold water, inside rock, in the ordinary chemistry of a young solar system. That part is now demonstrated rather than argued. But the selection, the decision to use one hand and discard the other, did not come from space. It happened somewhere on the path between raw chemistry and the first living cell. And we still cannot say where. We spent 7 years and traveled nearly 4 billion miles to bring back 121 grams of the darkest rock we could find. What we learned is that the raw material of biology is ordinary. It is sitting on asteroids. It has been sitting there since before Earth had a surface. Which means the hard part of the origin of life was never the ingredients. It was everything that came after.